So let's deal with, we are dealing with periodic classification and periodic properties, and I was actually trying to induce some degree of seriousness into you when I actually started the periodic classification. Now what I mean by degree of seriousness is, it's not that there are elements which are lying outside and someone gave you a job that you place these elements in an order in rows and columns. That's not the case. You must understand. You have driving principles, there are driving rules, there are schemes, the basis of which the periodic classification has been framed. It's not that as simple that someone has thrown the elements outside and you are placing them in rows and columns. It is absolutely so trivial is that thinking. That's what I'm trying to tell from day one when I was introducing periodic classification. In fact, I have summed up by telling you that in fact it stimulates research is the periodic table. Why I call it stimulates research? For the simple reason I have been mentioning every time that if you discover an element even 30 years from now or 40 years from now, you have the position of that particular element in the periodic table. And remember, even though the element is not discovered also, such properties prima facie can be evaluated right sitting here in the room. You must understand. So that's what I meant by stimulating what? Research. So the periodic table is open for you. You can also do the same thing, because I was telling you that each period which you are seeing, the horizontal lines, what you're seeing is a period, is a shell proposed by Bohr. So each period in the periodic table is nothing but a shell which is proposed by Bohr, or orbit, or non-radiating path, or whatever. And remember, an atom has an infinite number of shells, and when you consider a period to be a shell or an orbit, then you have infinite number of what? Even periods. And let me tell you that right now in the periodic table, you must understand that you have 7 periods, and the 7th period itself is incomplete. 7th period itself is incomplete, leaving a scope for you to go out, do some research, discover some element, and I have for you the position fixed for you in the periodic table. You must understand this, right? So you have a large scope, it stimulates research. No one has thrown these elements outside in your room, everywhere in your shelves, and you came here and you are placing them in accordance to what you wanted, or your wish, or something like that, someone wish. Remember, there are principles, there are schemes, and as I said, it stimulates research. Number one, which I wanted to into you, a degree of seriousness. So also I said that people who are periodic classification, people are good at periodic classification, they are good at chemistry. So what is the index for people who are good at science and in chemistry is you must be good at what? Periodic classification, and the entire chemistry revolves around what? The periodic classification. You must understand this, right? The other fundamental thing which I was telling you, there are 125 to 130 elements right now in the periodic table, and then what is the basic difference between all this? What is the basic difference between all these elements in the periodic table? If you ask me, then I would like to say, you ask me n number of times also, I would like to say it's basically size and nothing more than that. So why lithium is lithium, why potassium is potassium, why iron is iron, then I think it's all about sizes and nothing more than that. In fact, if you actually look into the basic law of periodic classification, then understand that it's nothing but the chemical properties and physical properties are basically functions of atomic size. And that's why when we were discussing periodic properties, we were dealing with atomic radii in the first place, because everything, every property, every single property, the behavior of each and every element, physically or chemically, are all functions of atomic size. If you have a bigger size, you have a certain set of properties. If you have a smaller size, you have a certain set of properties. It's all about what? Size. So the most fundamental thing about what? An element is nothing but what? Size. So we were discussing in the first place about what? Size. This is what I was telling. And when we are dealing with sizes, I told you that you have atomic radii. And remember, even the modern periodic law, I'm not interested in what people have done earlier, right? People have attempted several things, but I'm not interested in that. We are dealing with the long form of periodic table, in which you have 7 periods and what? 18 groups, right? 7 periods and 18 groups, the 7th period being what? Incomplete. Now, if you deal with that, then understand that, right, the atomic radii becomes the most fundamental thing. And I was telling you atomic radii definition seems to be idealistic, and I was proposing alternate definitions for that. And I was telling you covalent radii, I was telling you van der Waals radius, I was telling you metallic radius, and I was telling you about ionic radius. And for one definition, we have actually proposed 4 alternate definitions, indicating that the basis seems to be bonding, and there is no bonding, no single bonding in the entire periodic table, you must understand. So depend on that, I think I have covered the entire atomic radii for all the elements in the periodic table. This is the first thing I was telling. The second thing, yesterday I was telling about electronegativity. Right? And what is electronegativity? Electronegativity is basically a periodic property. Now what's a periodic property? A property that repeats itself at regular intervals in a period. Right? A property that repeats itself at regular intervals in a period can be called as what? A periodic property. You must understand this, right? And I was dealing with electronegativity, and I was clearly telling you that it's a relative tendency. It's not an absolute tendency. It's not an isolated phenomena. It's not an isolated phenomena. It's basically your tendency is measured with your neighboring tendency when you are actually participating in bonding. So whatever, whether it's a tendency or relative tendency, it doesn't matter. But I think tendency doesn't have any units. You must understand this, right? But somehow Pauling has attempted, and he has assigned numbers, basically he has assigned numbers, right, to each and every element, such that once you read that number, once you remark that number, you will actually get to know how much is the electronegativity power of that particular element. And in that process, we were assigned number 4, which is highest for what? Fluorine. And the 4 number is arbitrary. And if you want to get into details, I think I have done that in the previous lecture. You can get through that, right? Number 4 for fluorine, which is the highest in the periodic table. And then comes oxygen, then comes what? Nitrogen, and then halogens, and that's how it goes off. And let me tell you that electronegativity is something, it is something basically told for what? Non-metals, and not what for metals. You must understand. Electronegativity is told for what? Non-metals, and not for what? Metals. You must understand this, right? So if that is the case, let us take and today discuss periodic property number 3, and I call this to be electropositivity. Electropositivity. Let's define this. See, the sequence is what we will do is we define a periodic property. We will define a periodic property. Then what we will do, we will write the trend. Trend in what? How does it vary in a period or in a group in the periodic table? That is the second thing. Third thing, what we will do is go in for some of its applications. We extrapolate it such that you will see this in the exam. You must understand, right? So what we will do, it's time to define what is electropositivity. If someone is asking you what is electropositivity, first of all you tell him that it's a periodic property and it will be repeating itself in regular intervals in the period, right? That's number 1. Now if you want me to define this, then I would like to say the ease with which, the ease is also tendency. Ease is also tendency. You don't have any units for electropositivity. You must understand, right? So the ease means the ease, the English word ease means easy, the way you can easily do things, right? The ease. I would like to underline this. The ease with which an element loses electrons. Come on now. This seemed to be exactly opposite to yesterday's periodic property. The ease with which. Now when I say ease, the ease means it is easy for an element. It's easy for element. That's what is called ease. Right? Electropositivity, if you define the ease with which an element tries to lose electrons. Right? That ease. Now the ease will be more. If I can write some synonymous statements to you, ease shall be more, right, if electron is far away from nucleus, right, far away from nucleus. You must understand, when the electron is actually far away from the nucleus, it's in a relaxing mode, it relaxes, and it's easy for you to remove the electron because you are not within the clutch of the nucleus, you're just loosely held. You must understand this, right? So the ease with which an element loses electrons, ease shall be more if electron is far away from the nucleus. If I combine these two, what I understand basically, electropositivity is nothing but the ease, right? It seems to be a function of size again. And I was telling you this n number of times. You tell me any number of periodic properties, n number of periodic properties, they are all functions of size. So whether it's electronegativity, electropositivity, electron affinity, or whatever you will be discussing in the periodic classification, everything boils down to what? Atomic size. So even the ease with which an element loses electron seems to be a function of size, you must understand. And what is the exact relation between them? If you actually see that it implies that electropositivity is basically directly proportional to size. You must understand. It's directly proportional to what? Size, you must understand. So it indicates basically bigger the size, if I can write it, bigger the size, right, more is the ease. More is the ease which you are speaking of. Ease is the thing which is easy to do things. In this case, it's easy to remove electrons. So when you're actually having a bigger size, then more is the ease to remove electrons, and then more is electropositivity, you must understand. So it's a direct relation between electropositivity and size. That's what is called electropositivity. And let me draw your attention, as yesterday we were discussing about electronegativity, which is told for nonmetals. Electropositivity is told for what? Metals. And all nonmetals are placed to the extreme right of the periodic table, and then all metals are placed to the extreme left bottom of the periodic table. You must understand this. Right? So electropositivity is a language which is used for what? Metals. Electronegativity is the language which we use it for what? Non-metals. You must understand. So electropositivity depends on what? It depends on what? Size. It depends on size, and bigger the size, more is the ease to remove electron, and more is what? Electropositivity. If you know this, then I think it's easy to write the trend. If I can write the trend, how it varies in the periodic table, and if you see in periods, you can understand that the size decreases. The size is decreasing when you actually move from left to right. Right? The size is decreasing. So you can say that electropositivity also decreases because you have a direct relation between them. So electropositivity decreases even from LHS to what? So to the left to what? To the right in a period. Similarly, in groups, you can understand that the size increases. So thereby electropositivity also increases in a group from top to bottom, you must understand. Right? So from top to bottom, the size increases, the electropositivity increases. In a period from left to right, the size decreases, so thereby you must understand that even electropositivity decreases. Right? This is one of the periodic table property and the trend, which is the basic information what I'm giving. Let's go into some of the applications. I think that might be linked to your exam, what you will be writing. Like before I actually go there, watch carefully here. The ease with which, right, the definition, if I can read it for it, the ease with which an element loses electrons, right? And this ease shall be more if the electron is actually far away from the nucleus. You must understand. Right? So I can simply say you're basically telling me that electropositivity or the ease is a function of size again. Well, I'm not surprised, because every property what you will be discussing must be a function of size and nothing more than that. You must understand. So electropositivity and size are directly related. Bigger the size, more is electropositivity. So similarly, in periods, the size decreases, so electropositivity also decreases. In groups, the size increases, so the electropositivity also increases, right? So now what we will do is basically let us understand and go in for some examination details, and then we will see its we are now going to see its what? Applications, right? So if you can understand all this, keep this in mind. And now I go for the applications of electropositivity, which will be some of the questions in your exam. You must understand this. Let's see. some of the applications of electropositivity, right? Applications. Applications of electropositivity, right? Understand, where do we use this? Where do we use this? So electropositivity is one of the things which will determine the basic what? The basic thing of what? Metals. You must understand all the properties of metals, what you see in the periodic table. Name any metal, their properties, they will be linked to what? Electropositivity. You must understand this, right? If that is the case, let us take up one of the cases, and this is, let us link this with electrolysis. Let's link this with electrolysis. These are all now the questions which will be asked in your JEE exam, so I draw the attention of everyone, please. I draw the attention of everyone. That is the basics, what I told you. Electropositivity depends on what? That is the thing. Now what we are trying to do is take up some of the applications which will be asked in the exam. And the first thing what I wanted to take up is electrolysis. You must understand. You know, electrolysis, since electropositivity we are dealing with basically metals, right? We are dealing basically with metals. In periodic table, what happens is, there is a method for extraction of the metals, right? And in the method of extraction of the metals, I think some of the metals are extracted through different means, and some of them have a different means, and you have several ways to extract what? Metals. There is no single method to extract what? All the metals with the same procedure. You must understand. And as far as the metals are concerned, the metals that are placed to the extreme left of the periodic table, that's nothing but the first group and the second group. The first group and the second group elements, that is alkali and alkaline earth metals. You know, they seem to be extremely electropositive, because if you see the elements that are placed to the extreme left, if you actually see extreme left of the periodic table, they have the largest sizes, you must understand. So if someone is asking me the biggest sizes are present in the periodic table, they are to the extreme left, you must understand. So when you are biggest in the periodic table, then I think your electropositivity will be what? More, you must understand, right? If that is the case, as I told you, for the metals, you have various methods for extraction of metals, right? For the more electropositive elements, that is your first group and the second group, are alkali and alkaline earth metals, people use electrolysis. You must understand. Electrolysis is the method employed for extraction of metals for more electropositive elements. Now, where are the more electropositive elements? They are placed to the extreme left bottom, that is alkaline earth metals and alkali metals. These two people employ the procedure that is electrolysis, right? And suppose for the D block elements, they go for pyrometallurgy. That means extraction of metals at what? Higher temperatures. Right, higher temperatures. And then you have metals, noble metals like gold, silver, and all this, they are extracted at room temperatures. That's called hydrometallurgy, you must understand. Right, and we have, like that you must understand, for each and every metal, we specify a certain method for extraction of them. And in that process, electrolysis is one of the methods to extract what? Metals, and this is employed basically, I can write it for you. This method is basically employed for extraction of high electropositive or more electropositive metals. You must understand. And that I refer to be the first and the second groups in the periodic table, that is alkali and alkaline earth metals. It itself is a question in the exam, right? You have several methods for extraction of the metals, and the metals that are more electropositive are extracted through electrolysis as the phenomena, and then if they are less electropositive, like in the case of D block, they are extracted through a method called pyrometallurgy. That is extraction of higher temperatures, extraction of metals at higher temperatures. That's nothing but what? That's what happens in your steel plants, right? So that's extraction of iron at what? Higher temperatures. That's what we do it in furnaces, right? And we have certain elements like noble metals like gold and silver. They will be extracted at what? Room temperature, and such a method can be called as what? Hydrometallurgy, right? So what I'm telling is, in all, You have several methods for extraction of metals in the periodic table, and electrolysis is employed. It's employed for extraction of more electropositive metals like first group and second group, you must understand. Right? Now what I'm doing is I'm linking this with electropositivity, as I said in the first place, that itself is a question that first and second groups are extracted through electrolysis. Right? That's number one. Number two, what I mean is this. Remember, and I wanted this to be highlighted for you. And I'm highlighting this. That is the reason I have taken this for discussion. Right? Remember this. Remember, and this is a sweeping statement what I'm making. You cannot, mind you, I draw the attention of everyone. I draw the attention of everyone, please. Right? I'm telling you, you cannot, right, extract. You cannot extract, right? Alkali, when I say alkali, I'm referring to the first group, the second group elements. That is alkaline earth metals. This is alkaline earth metals, that is I'm referring to the second group, you must understand. So what I'm basically telling is you cannot extract alkali and alkaline earth metals by electrolyzing their salt solutions, or I can simply say aqueous salt solutions. Their aqueous salt solutions. You must understand this. First of all, what we are doing is we are going in for applications of electropositivity, in which I am taking electrolysis as an example. Well, in electrolysis, you must basically understand that several metals in the periodic table will be having several methods for their extraction. And one of the extraction which is exclusively only for first group and second group is electrolysis. Electrolysis is a non-spontaneous process where you will be employing for the first and second groups by using an external aid, that is nothing but the electric current. You must understand. So electrolysis is the word which is used, is the method which is used for extraction first group, second group elements. This itself is a question in exam. You must understand. The second thing what I'm telling is basically I draw the attention here. And what I'm telling, you cannot extract. It's not about extraction. You cannot basically what? Extract. You cannot extract. Cannot extract alkali or even alkaline earth metals. So you cannot extract alkali or even alkaline earth metals by electrolyzing. There, I would like to underline for a few minutes here, their aqueous salt solutions. You must understand. There is and then why I am discussing this, because this we will link it to electropositivity. Electropositivity, you must understand this. Right? So two things you need to carry forward in your brain. That's number one is the electrolysis, is the procedure to extract each and every element in the first and the second group, and those are labeled to be the most electropositive elements in periodic table. Right? So for most electropositive elements, it is electrolysis, which is the due procedure to be followed. That's number one. Number two, while you employ electrolysis, you must understand you can never extract an alkali metal or even alkaline earth metal by electrolyzing their what? Aqueous salt solutions. This is the second thing you must remember. Now, why, if you ask me, why such a case, then I think we have an explanation which I would like to give it for you. Shall I? Observe carefully here. Observe. Observe. So what I'm telling basically is, for the first group and even the second group, it's basically exclusively electrolysis is the best. Is used for extraction of the first and second group. It's exclusively the electrolysis which is employed. Employing the remaining thing is stupid rather, right? Please don't do that. And then exclusively if it is done that, and here the only caveat is basically don't use aqueous salt solutions. Aqueous salt solutions. Don't use aqueous salt solution for extraction of the first and the second groups. If you ask me why, then here is the explanation what I'm giving, right? Observe what we will do, and I'm actually comparing two things. Here I go for electrolysis, observe carefully, of aqueous NaCl. Here I go for the electrolysis of aqueous NaCl. And I wanted to compare this with electrolysis of molten NaCl. Now when I say molten NaCl, it's pure NaCl without water. Now what do you mean by molten is, I have melted it down to its melting point. So sodium chloride has a melting point and I have melted it and it has become now a liquid. That's what I call this to be a molten NaCl. Molten NaCl doesn't have water. In the first case, I am going in for electrolysis of aqueous NaCl. How do they both work? I'm just comparing one next to the other. And it is something linked to our periodic property that's nothing but what? Electropositivity. And I draw the attention. In the first case, what is happening? The cations, what you get, look into the cations, what are they? Because NaCl is an ionic compound. When you put NaCl in water, it ionizes, right? So the electrolyte will be having these ions. So you look into the cations that are positively charged, you have H plus and you have Na plus. Now where do we get H plus from? H plus from water and Na plus from NaCl. You must understand. So since you have taken aqueous NaCl, the aqueous part, the water part is giving you what? H plus, right? And the NaCl part is giving you what? Na plus. And I am restricting my discussion only to cations. Why I am restricting my discussion only to cations? For the simple reason, cations are only formed by metals. They don't form, non-metals don't form cations. You must understand. It is only the metals which vomit what? Electrons. So the vomiters of electrons are nothing but metals, and only metals form what? Cations. So we will restrict our discussion only to what? Cations. Now if you see, these are the cations, H plus given by water and Na plus given by what? NaCl, right? Now what you do in electrolysis, what is happening at cathode? Now what is cathode? It's negative. Cathode is negative. It is electron-rich substance. Electron-rich substances are called what? Negatives. That's cathode, right? So in electrolysis, you have cathode, anode, and all these things, right? So I am restricting myself to only cathode because I'm dealing only with cations, because only metals form what? Cations, you must understand. So at cathode, if you see, right, since this is electron-rich, both these cations, since they develop a positive charge, they have a positive charge, they try to run towards cathode, right? Positive charge is a sign of electron deficiency. That means you are hungry for electrons. When you are hungry for electrons, you reach the cathode because it is electron rich. You have a food there, right? So what they do is, when you switch on, at cathode what is happening is, the H plus and Na plus both run towards what? Cathode. They both run towards cathode because both are hungry. They both run towards what? Cathode. Because both are hungry. But more hungry. Naturally, the fellow who reaches the food center first should be more hungry. The fellow who is not hungry will reach last. It's a common sense, right? You are actually going in for a pizza, then the fellow who is hungry will reach the Pizza Hut first, right? As simple as that. Chemistry is no different. So both are actually running towards what? Your cathode, but it is only the fellow who is more hungry reaches what? Cathode first and deposits first, but more hungry H plus deposits. So it's basically the H plus which goes first, eats the electron and forms hydrogen, and then it forms hydrogen gas. You must understand. What is strange here, what is surprising here is when I am going for aqueous NaCl electrolysis, people expect sodium to be deposited, and see what has happened. Sodium was not deposited. See what exactly happened here. At cathode, which is negative, both H plus and Na plus is running towards the cathode. But as common sense is suggesting, it is more hungry H plus which deposits first. Now what do you mean by more hungry? Why such a thing happened is the issue. Now if you look into this, sodium is nowhere. It is left out in the tank, but it is the hydrogen gas which is liberated at cathode. That might be a question in the exam. During electrolysis of aqueous NaCl, the gas that is liberated at cathode is hydrogen. The gas that is liberated at the cathode is hydrogen and not sodium. The substance that is deposited at cathode is hydrogen and not sodium. The sodium ions are left out in the tank. Now if you ask me why, then the explanation is this. Now if you look into this, if you look into both of this, now why? Now that's what I'm telling. So you understand that electrolysis of aqueous NaCl, the product at cathode is not sodium, which is very strange. It is basically what? Hydrogen. Now why such a thing happened? I would like to label it off perfectly, you must understand. Now why such a thing happens is, if you look into this here, so I can simply say this you remember forever. This you remember forever, right? More electropositive deposits last. You must understand. More electropositive deposits last. So out of H plus and Na plus, both are running towards cathode, but the one which is more electropositive is sodium. The one which is more electropositive is sodium, right? It's more electropositive. More electropositive means it's vomiting electrons. When you vomit electrons, can you eat? When you're vomiting, say, you have that vomiting sensation. Can you actually take some more food? Absolutely not. Similar is chemistry. Out of H plus and Na plus, the Na plus is more electropositive. More electropositive means it is vomiting electrons. When it's vomiting electrons, it reaches the cathode, which is the electronic source. It reaches the cathode last. So it is the hydrogen which is actually deposited. Strange. So I want you to remember till you die that simply more electropositivity always deposits last. So there is a competition, if there is a competition between, right, Na plus, H plus, K plus, Rb plus, or even the entire first group elements are with hydrogen. It is always the hydrogen which deposits first. It is never sodium, it's never potassium, it's never rubidium, never cesium. Cesium being the highest electropositive element in the periodic table, even that doesn't get deposited. So simply speaking, more electropositive element in electrolysis deposits last at cathode. Is it not an application of electropositivity? That's where you need to extrapolate your subject when you're actually preparing for JEE or even medical entrance examinations, you must understand. So one sweeping statement which I wanted to make is don't use aqueous salt solutions for extraction of what? First group and second group elements, because it is always the hydrogen which is liberated at cathode, not the first group and the second group elements. So simply speaking, in the examination he is asking which of the following is true, which of the following is true, which of the following is true, then the answer would be more electropositive deposits last. It's more electropositive deposits last, right? When we are speaking of such pinpointedly something about like this, right? More electropositive deposits first, and you cannot extract first and second group elements. Well, then people will ask you, then I wanted to extract alkali metals. What shall I do? Well, I wanted to extract what? The sodium and potassium. And you are telling that in aqueous salt solutions you can't do that. So what shall I do? Shall I run away? No, absolutely not. We don't run away. But the only thing we should taking care of is basically is this, right? In electrolysis, a molten NaCl, it's molten. It's molten NaCl. It's without water. Without water. Ensure that the water is not there. You always have sodium. Then what happens is at cathode, you can simply say at cathode which is negative, it is only the sodium which is deposited. And you got your sodium. So, for extraction of alkali and alkaline earth metals, you must be taking molten salt solutions and not what? Aqueous salt solutions, you must understand. Now, what happens is the questions which are asked in the exam will be much specific, more specific. You must understand, because you are writing this exam after finishing the first year as well as second year. So, he will be linking chapters. You must be careful here. So, he'll be more specific. Like the same thing what I'm telling here, the subject points which I'm discussing it with you, they can be more specific for you. Now, what do you mean by more specific is this. For example, now what I will do, instead of asking all this, you must understand this. Right? You must understand this. These are the summary of things what I'm speaking of. Summary of things, questions that might be asked in exam. These might be the questions which are asked in exam. These are the questions which I wanted to summarize what I'm telling. The applications of electropositivity. The first thing what I wanted to say, the first group, second group, these are the more electropositive in periodic table. These are the most electropositive elements in the periodic table. Right? If that is the case, then understand. Then if that is the case, first and second extracted via electrolysis only. Electrolysis only. So which of the following element electrolysis as a method is used for extraction of that particular element? The answer must be electrolysis. Third thing what I wanted to quote is first and second groups use molten salts. And you don't use not aqueous salts. Don't use what? Aqueous salts. Right? And if you use molten salts, then molten salts used, then you get first and second group deposited at cathode. The first and the second groups deposited at what? Cathode. Straight away if you use molten. If you use aqueous, then it is hydrogen deposited at cathode. And not first and the second. And not what? The first and the second, you must understand. It's not first and the second. Right? If that is the case, then also understand that's the reason why. That is the reason why. Right. That is the reason why. This is the specific thing which he will be asking. Specific thing which he will be asking. Right? So that is the reason why Downs process, and I draw the attention for everyone. It's the Downs process. Now Downs process is for what? Downs process is for extraction of sodium. Downs process is for extraction of sodium metal. And sodium metal belongs to what? The first group. And he wanted to extract an first group element. Now if you want to extract an first group element, use molten salts. Use molten salts. Not what? Aqueous. So Downs process uses molten NaCl, you must understand. It's molten NaCl, you must understand this. Right? It's molten NaCl. If this is the case, if I can put the subject point properly, then understand this. Before I rub this, this is the gist of what my discussion is regarding electropositivity. Right? It's an integrated approach what I'm taking. You can't just discuss the electropositivity of the periodic table, tell the trend in the group, tell the trend in the period and run away. Since you're writing your exam, you must be linking this with each and every chapter wherever there is use. And that's what I call it to be an application. You must understand. Right? So first group, second group, more electropositive. The best method is what? Electrolysis. Use molten salts and not aqueous salts. Molten salts, the first and second group are deposited at the cathode. And aqueous salts, you always get hydrogen. And the reason is, that's the reason why Downs process used for extraction of sodium is molten NaCl is used and not aqueous NaCl, you must understand. If you wanted much clarity, then what I will do is as simple as this. Watch carefully. Right? If this is the case, if there exists, right, H plus, Na plus, K plus, Rb plus, and Cs plus. H plus, Na plus, K plus, Rb plus, and Cs plus. All these are there in the tank. In the electrolysis tank. In the electrolysis tank. Then order of deposition. Then the order of deposition, because these are all positives, deposition at cathode, mind you. At cathode, the order of deposition of all these cations at cathode. What will be the order? Well, I was telling you very clearly. Use this, no? I told you. More electropositive deposits last. It deposits last. Then if this is the case, then if I can write the electropositivity trend in all this, then I think the Cs plus is the highest electropositive compared to Rb plus, compared to K plus, compared to Na plus, compared to what? H plus. You must understand. That is the order of electropositivity. The highest is what? Cs plus. That means it vomits more. Vomits electrons more. And I was telling you, when you're vomiting, will you eat? You're vomiting already. You're vomiting because you have eaten till here. And someone is offering you pizza at that time, I think you don't eat. Because you are already having the sense of what? Vomiting. So the more electropositive element, that is the cesium which vomits more, deposits last. So if you look into the order of deposition at cathode, well, remember the order is, it is H plus which will deposit first, then comes what? The sodium, then comes what? Potassium, then comes what? Rubidium, then comes what? Cesium, and this deposits last, and this deposits first. That deposits first. That is a subject point which I wanted to convey to you, you must understand. And remember, we are discussing electropositivity. Electropositivity is the ease with which an atom loses electrons. The ease will be more if the size is more. So ultimately you are boiling down to size. Electropositivity is a function of what? Size. Size decreases in a period, so electropositivity decreases. And the size increases in a group, so electropositivity increases. Right? And if I am extrapolating this as an application, then I think during electrolysis, which is a method which is employed for extraction of the first and second, it's always the hydrogen that deposits first if you're using aqueous salt solutions. So that's how it is. That is the order. I think I'm clear here, right? That is the first application which I'm quoting. Now getting into the second application, right? And I draw the attention of everyone, please. Watch carefully the second application. Application number 2. Application number 2. Application 2. Now what is application 2 of electropositivity is basically, look into the definition what we are telling. What are we telling electropositivity to be? Application number 2. Electropositivity application number 2. Mind you this. Electropositivity application number 2. Now what are we dealing with? Now electropositivity, recollect the definition. What did we say? The ease with which you lose an electron. So simply speaking, in our simplest of the languages to understand, if you can vomit the electron on your neighbor, right? The greater the tendency of vomiting electrons on your neighbor, the greater the tendency of vomiting electrons is called electropositivity. If that is electropositivity, then I think I would like to link, I'm linking reducing power. I'm linking reducing power with electropositivity. I'm linking reducing power with what? Electropositivity. You must understand this. At the same time, there are theoretical ones, but there are some caveats also which are asked in exam. Right? If this is the case, what is the linking reducing power with electropositivity is first of all, what is reducing power? Well, I would like to say reducing power is a function of electropositivity. Electropositivity is the power to vomit electrons. Now, what is reduction? In our earlier classes, we were told, if you add electrons, then you are reduced. If I am adding electrons to myself, I am reduced. If an atom adds electrons to itself, then the atom is reduced. Substance plus electrons is reduction. Must understand that, right? If this is the case, then reducing power and electropositivity, it's a function of electropositivity, and I can give you the relation rather, reducing power is basically directly proportional to electropositivity. You must understand. Greater the electropositivity, greater is the reducing power, and this is theoretically. This is theoretically, it's correct. Yes. If I am there, if I possess the greatest vomiting power, then if I vomit electrons onto you, you are reduced. When you are reduced, I am a very good reducing agent. My reducing power is more, right? So, if the vomiting power is more, then the reducing power is also more. You must understand. If this is the case, then understand here, right? Reducing power directly proportional to electropositivity, and electropositivity directly proportional to size. That's what we were telling. If this is the case, then it also implies reducing power is directly proportional to size. It's directly proportional to size. Because you are proportional to EP proportional to size, and reducing power is also proportional to size. So it means that bigger the size, greater is the reducing power. If this is the case, it implies left to right in a period, then EP increases, left to right, the size decreases. The size is decreasing in a period. So naturally what? EP will decrease. So I can simply say even RP decreases. size decreases from left to right. So the vomiting tendency decreases from left to right. So the reducing power must also what? Decreases from what? Left to right. And then it also implies from top to bottom. From top to bottom, the size increases. The size is increasing. So electropositivity increases. Then even reducing power increases. You must understand. You must understand this. Right? So basically I'm trying to link reducing power with electropositivity. Look into this. What is very strange here? What is very strange here is you quote any periodic property. You quote any periodic property. They are all linked to sizes. Ultimately, it boils down to the size. So that's why I said all physical or chemical properties, what you discuss, are all functions of size. That's why while discussing periodic properties, we were putting atomic radii in the first place, size in the first place. So similarly, right, this is again proportional to EP. That's a trend in what? A period. A trend in what? A group from top to bottom or left to right. Those are the trends. Then if that is the case, then what is that we wanted to know here? Now what is that we wanted to know? Watch carefully here. Watch carefully here. Yes, watch carefully. Theoretically, now which theory? The theory which I am discussing. The theory which I am discussing. Theoretically, then I can simply say most now I can simply say like this. Biggest sizes in periodic table are the first group and the second group. Biggest sizes are the first group and the second group because they are placed to the extreme left in the periodic table. And left to right, the size decreases. Left to right, the size decreases. You must understand. So, biggest sizes in periodic table are first and second groups. If they are the biggest sizes, then electropositivity highest. It is highest for first and the second groups. They will be the highest. So the highest vomiting tendency is basically for what? The first and the second groups. That is, the highest vomiting tendency is nothing but what? Electropositivity. Or simply speaking, or I can simply say reducing power even highest for the first and the second groups. So it implies that alkali, alkaline earth metals are the best reducing agents. You must understand this. They are the better reducing agents. You must understand this. So where are the best reducing agents placed in the periodic table? They are again coming to the left. You must understand. So if I can write a trend for you, then it is like this. Right? This is basically theoretically. Theoretically, that is how it is. Right? But these things won't be so simple in the exam. They won't be so simple in the exam. What I will do, I'll stick to what I'm telling, and then I reason with myself, and then from there we evaluate one more question which is important in the exam. Now, first of all, stick to the theory, and then if you see, given the first group elements, now if you look into the first group elements, then it is lithium, it is sodium, potassium, it is rubidium and cesium. These are the first group elements. First group. Right? From top to bottom, the size increases. When the size increases, electropositivity increases, reducing power should increase. So what I will do, I'll put all the three. If you look into the size, then lithium is the smallest of all compared to sodium, compared to rubidium, compared to cesium. You must understand. That is the size trend of the first group. If the size is more, then electropositivity is more. So what I will do, if you find electropositivity, then it is lithium, which is less electropositive because both are directly proportional. Less than sodium, less than potassium, less than rubidium, less than cesium. And electropositivity is proportional to reducing power. So if this is also proportional to reducing power, then I would like to write lithium less than sodium, less than potassium, less than rubidium, less than cesium. So we conclude simply, cesium is the best reducing agent. Best reducing agent, all these seem to be in a given conditions, that is theoretically. Now what is theoretically? That's nothing but through vomiting tendency. You must understand. So the highest vomiting tendency is basically possessed by cesium. So if cesium possesses highest vomiting tendency, it must be labeled as what? The best reducing agent that is available in chemistry. Simply hanging on to what? Vomiting tendency, because electropositivity is nothing but the vomiting tendency what we are speaking. But to your surprise, let me tell you, this is the question which is asked n number of times in your exam. There's nothing wrong in this. There's nothing wrong in this theoretically. Cesium is the best reducing agent theoretically because it's vomiting tendency which determines what? Reducing power. But let me tell you, in fact, in an aqueous medium, it's lithium which is a powerful reducing agent. What? We are surprised. We are exclamated. Theoretically speaking, there is absolutely nothing wrong. Cesium has the highest vomiting tendency. So it must be labeled as what? Highest reducing power. But in fact, what I am telling is in aqueous medium, it is lithium is the powerful reducing agent. And what is surprising, lithium is the smallest in size. Well, if that is the case, then for reducing power, it's not exclusively the vomiting tendency which plays a role. There are other things, right, which are actually determining the reducing power which is asked in the exam. It's almost like, in spite of you getting in mathematics 40 marks out of 100, but still you stood first in the class for the simple reason because you scored 100 out of 100 in all the other subjects. It's something like that. So getting first in the class, you need not get 100 out of 100 in mathematics. Alone. Right? Since you fared well in the others, I think you got through. Such an explanation is required for lithium, which we will be dealing for sure, and will give you a detailed explanation. Right? You must understand.